I welcome all of you to the class. In the previous class, we were talking about the Castigliano's theorem, and in today's class, we will continue from the previous lecture. Okay, so the topic that we are discussing last time was we are trying to find the deflection. Sorry, we are trying to find the deflection and slope of beams, deflection and slope of beams, and we were using Castigliano's theorem. As far as the Castigliano's theorem is concerned, in Castigliano's theorem, we have two forms. One is called the Castigliano's theorem 1, and another one is called the modified Castigliano's theorem. Okay, so what the theorem is all about, let's suppose we are having a cantilever beam. Let's talk about a beam. And let's suppose the length of the beam is, say, for example, L. Okay, at L by 2, a point load is acting. Let's call that as point load P. Just a minute. And or let's take this load at one of the ends. Let's suppose we have a load. Let me rub this entire one. We have a cantilever beam, and this cantilever beam is subjected to a concentrated load at its free end, as well as it is subjected to a bending moment. Okay, in an anti-clockwise direction. The magnitude of this moment is, say, for example, M, and the magnitude of this load is, say, for example, P. This entire length is given to us as L. Okay, and let's suppose this is point A and this is point B. Fine. Now the question says calculate the slope and deflection of the deflection curve at point A. Fine. That is, we have to find the deflection at point A, that is delta A. We have to find the slope at point A, that is theta A. That is, if you look at the deflection curve may be, say, for example, like this. Okay, now how much is the deflection at point A means how much has this point B moved downwards. Okay, how much is the deflection at point A, and if you draw a tangent at point A to the deflection curve, how much angle it will subtend with respect to the horizontal, that is theta at A. So we have to find theta at A, we have to find delta at A using the Castigliano's theorem. So first and foremost thing is that we have to find the bending moment M. Okay, so what you do, you take a section out here and assume that the bending moment here is shear force is V and bending moment is M as a function of X. Okay, let me call this bending moment as M naught. Okay, so when you calculate all the moments about an axis passing through this point where you have drawn this section, then this M comes out to be equal, you can verify it, it will be equal to minus P into X. That will be moment because of this P, that's P into X, because you are taking a section at distance X, and plus minus M naught. This will be, let me call this as equation 1, and that's quite evident because when you take moments about an axis where you have taken the section, the first moment will be P into X, and that is anti-clockwise. You will take that as positive, and you also have the anti-clockwise moment here, that is M naught, that is plus M naught, and you have this anti-clockwise plus M of X is equal to 0. Therefore, if you look at M of X will come out equal minus P of X minus M naught. Okay, that's what we are writing over here in the form of equation number 1. Okay, now after calculating the moment, calculate the total strain energy. Total strain energy of the beam is given as integral going from 0 to L M square dx divided by 2 times EI. That will be equal, in place of M, you have to write this entire expression. This will become 1 by 2 times EI, 1 by 2 times EI, integral going from 0 to L, minus Px minus M naught whole square d of X. Okay, that will come out to be equal, this is P square L cube. This will be P square L cube by 6 times EI. 6 times EI plus P times M naught L square divided by 2 times EI plus M naught square L divided by 2 times EI. This is the total strain energy of this beam. Fine. Now, once you have calculated the total strain energy of the beam, then it's quite important to find that deflection at point A, delta A, that will be equal to du by dp. Okay, fine. That is equal differentiation with respect to p. So that becomes equal to PL cube by 3 times EI plus M naught L square divided by 2 times EI. Okay, this is the deflection at point A. This is the value of deflection at point A. Now, the slope at point A, theta A, will be equal du by moment at point A, that is du by dm. Okay, so you have to differentiate this u with respect to m. That comes out equal to PL square by 2 EI PL square divided by 2 times EI plus M naught L plus M naught L divided by EI. Okay, this is the value of theta at point A. So we have found we could calculate theta at A and we have calculated delta at point A. Okay, in the same way, let's take one more example. Let's again talk about a beam, and this beam happens again. Let's take again a cantilever beam, though we can apply this term to beams which are not cantilever. Okay, let's take a cantilever and let's suppose that it is subjected to, again, the same type of example I will be taking. It is subjected to concentrated load as well as a moment at the free end. Okay, let's say this concentrated load is P. A moment here is M naught, as is given in the previous example. This is A, this is point B. Let's now demarcate this entire beam by a point. Let's say we are having a point here, that's point C. Okay, such that this dimension is L by 2 and this dimension is also L by 2. Okay, so this comes out to be, this is L by 2, this is L by 2. Fine. Now the question is, find the deflection and slope at point C. Find theta C and find delta C. This is quite important for all of us to realize, because now the problem is when you are finding the deflection at point C and the slope at point C, you don't have any point load acting at point C. Okay, you don't have any moment acting at point C. Fine. So the problem is when you find theta C, you will first of all calculate the total strain energy, then you will take differentiation of total strain energy with respect to the load. I will write that as P, but acting at point C. Let me write the D subscript. This is a load acting at point C, but we don't have a load acting at point C. Fine. Similarly, we will write dm du total strain energy differentiation with respect to the moment acting at point C. But the problem is we don't have any moment, external moment acting at point C. We don't have any external load acting at point C. So what to do? So when you have these types of problems, you are asked to find the slope and deflection at points where neither concentrated load is acting, where neither moment is acting. What you do, you apply what is known as a fictitious force and moment. Apply a fictitious moment, apply a fictitious moment and a fictitious load, and apply a fictitious load. Let's suppose at point C, let's suppose what we have, let's assume that at point C, we are having a concentrated load acting. First, for deflection, let's suppose we are having a concentrated load acting. Okay, and let's call this load as Q. Okay, this is, but this load is a fictitious load. It does not act anywhere. Okay, so when we are trying to apply the fictitious load, fine, then this fictitious load is to be understood that this fictitious load is not acting. Okay, we are just assuming that it is acting on the beam. Fine. So what we do? So based on this fictitious load that we have taken here, okay, calculate the total strain energy of the beam. So for us, Q is equal the fictitious load. I will write here Q is the fictitious load. Okay, it's not acting. We're assuming that it's acting on the beam. Now, what we will do, just a minute, what we will do, we'll find the total strain energy of the beam. Now, the total strain energy of the beam, now we are having concentrated load acting here. Okay, now you know, whenever there is a concentrated load acting on the beam and you have to find the bending moment in the beam, then you have to divide the beam on the two portions. One portion on the left hand side of this concentrated load, and another is the right hand portion of the portion on the right hand side of this concentrated load. So we'll write, so for the region going from for the 0 to L by 2, for this region, half region, write down the bending moment equation. The bending moment equation will come out to be equal to m as a function of x will be equal to minus m naught minus p into x. This is for this region. Now for this region, what will be the strain energy when you take the moment over here, when you derive the section out here? So for 0, for L by 2, for the region between L by 2 to L, okay, the bending moment equation, m as a function of x, let me call this as m1, okay, because this is in this region. Let me call this as m2. This m2 comes out to be equal minus px minus m naught. You can do it. You have to draw a section out here and take the moment about an axis passing through here, minus q into x minus L by 2. Okay, this is the moment in the second portion. Fine, this is the moment in the second portion. Now what we'll do in this portion AC, calculate the total strain energy in portion AC. The total strain energy in portion AC will be equal integral going from 0 to L by 2. Okay, m1 square, which is a function of x, dx by 2ei. Okay, so that is equal, in place of m1x, you have to write this expression that will be 1 by 2 times ei. I will write the final expression. Okay, integral going from 0 to L by 2 minus m naught minus px whole square d of x. Okay, that comes out equal, that is equal p square L cube by 48 ei, p square L cube by 48 ei plus pm naught L square, pm naught L square by 8 ei plus m naught L square, m naught square L divided by 4 times ei. This is the strain energy in the region AC. Now, in the same way, let's calculate the total strain energy in the region CB. That will be equal integral going from L by 2 to L. Okay, m2 square, that is minus px minus m naught minus q square dx divided by 2 times ei. The total strain energy in this region comes out equal to 7p square L cube. This is 7p square L cube by 48 ei plus 3p m naught L square by 8 times ei plus 5pq L square by 48 ai plus m naught square L divided by 4 times ei plus m naught q square divided by 8EI plus q square L cube divided by 48EI. This expression is for the strain energy in the region CB. Since strain energy is a scalar quantity, okay. So what will be the total strain energy? The total strain energy will be the addition of all these terms. Okay. So the total strain energy, I will write here, the total strain energy will be equal UAC plus UCB. Okay. That comes out equal to the total strain energy becomes equal to, so we have to add these two expressions. Okay. So let me clear some space over here. The total strain energy is a scalar quantity, we can add it. The total strain energy becomes P square L cube, P square L cube by 6EI, P square L cube by 6 times EI plus PM naught L square, PM naught L square by 2EI plus 5PQ L cube by 48EI, 5PQ L cube by 48EI plus M naught square L by 2EI plus M naught square L divided by 2EI plus M naught QL square by 8EI, M naught QL square divided by 8EI plus Q square L cube by 48EI, Q square L cube divided by 48EI. Okay, so this is the total strain energy. Now the things are easy for us because once we know the total strain energy, we'll directly use the Castigliano's theorem. Now the Castigliano's theorem says, in order to find the deflection at point C, what we have to find? In order to find the deflection at point C, we'll directly write the expression that deflection at point C will be equal to du by differentiation of total strain energy with respect to load at point C, that is Q. So once we perform du by dq, it comes out equal to 5PL cube. This becomes 5PL cube by 48EI, 48EI plus M naught L square divided by 8EI plus QL cube by 24EI plus QL cube by 24EI. This is very important expression. This is the deflection at point C. But at point C, how much is the load? Q. But Q does not act because we are saying Q is a fictitious load. So Q has to be equal to 0. So in this expression, put Q equal to 0. We will get du by dq at point C will become equal 5PL cube by 48EI plus M naught L square by 8EI. That's it. So we have found the deflection at point C where no load was acting. But this was done when we used what? When we used the fictitious load. In the same way, once you have done this part of the analysis, do the second part. That is, remove this Q. Now apply a fictitious moment at point C. Okay. So apply a fictitious moment at point C and call that moment at point C as MC. Do this analysis again. That is, now find the strain energy in the portion AC, find the strain energy in the portion CB, add up the two strain energies to find the total strain energy. Then do du by dm. Okay, that will give you the slope at point B, but you have to put MC equal 0 as we did here. So this is how we find the slope and deflection in the beam using the Castigliano's. That is very important expression. Sometimes we do what's known as the modification of the Castigliano's theorem. That is which I should slightly touch. If you look at the total expression of the strain energy, we write U is equal integral going from 0 to L m square dx by 2 times EI. Fine. Now, if we have to calculate the deflection at a point like A, we will write du by load acting at point A, let that load be P. We write du by dP. So that is equal d by dP of integral going from 0 to L. In place of U, we'll write m square dx by 2EI. So we can do what's known as differentiation under the sign of integration. Differentiation under the sign of integration. Okay, differentiation under the sign of integration. So what does this mean? We can write deflection at point A is equal integral going from 0 to L, differentiate m with respect to P. So it will be 2m, 2 and 2 will get cancelled. It will be m dx by EI. Okay, so this is also an expression used to find the what is known as the deflection at a point. Okay, so you can perform the differentiation under the sign of the integration to find this. Okay, oh sorry, you have to do so this expression needs a little modification. I have not done it correct. Sorry. So once you perform differentiation under the sign of integration, it will be delta A will come out equal. So differentiate the internal terms inside the integral term. So it will be integral 0 to L. Differentiation of m square will be 2m. And internal differentiation, that is dm by dp. dm by dp. And we have our dx by 2EI. So that comes out equal integral going from 0 to L m dm by dx, dm by dp, integration with respect to x by EI. Okay. Okay, so this is also an expression used to calculate the deflection at point A. We can also calculate the slope at point A by taking d by dm acting at point A. Let me call this dma. Integral from 0 to L m square dx by 2EI. That comes out equal to integral going from 0 to L m by EI. dm by dma. dm by dma dx. This is also an expression, and these expressions, when we perform differentiation under the sign of integration, this is called modified Castigliano's theorem. This is called the modified Castigliano's. This is called the modified Castigliano's theorem. Okay, so we can use this expression, or we can use this expression to calculate the deflection and slope in case of beams. Thank you very much.